All right, so we have this graph. It's got all kinds of goofy stuff going on at each of these x values, and then we went over and wrote them. Now at x equals -3, we can see that the limit from the left and the limit from the right are both equal to 0, which means that the overall limit is also equal to 0. However, the value at -3 is not the same as the limit. It's a different y value. And so when you have the limit, which is 0, being different than the value, which is -4, we would say that there is a point discontinuity. There is a hole in the graph. By the way, the limit does exist here. We'll talk about that a little bit later in the next video. Now at x equals 0, we have a limit from the left equaling 2, but a limit from the right equaling 3. Now here we see that the left and right hand limits are different, which does mean that the overall limit does not exist. But as far as discontinuities go, this would insinuate that there is a jump in the graph. And again, there's a jump in the graph because the left-hand limit is different than the right. The y values, you have to jump between those y values. At x equals 2, we have a familiar occurrence. It's obviously a vertical asymptote. And we can denote that by saying that the limit is equal to infinity. Now, when the limit is equal to infinity, that also implies a discontinuity. The discontinuity would be an infinite discontinuity. Each one of these limit statements describes a discontinuity. A point discontinuity, a jump discontinuity, and a infinite discontinuity. We'll talk more about each of those in the next video, but I want you to take a look at x equals 4 because it does not describe a discontinuity. You should notice that the limit is 2, but the value is also 2. And when the limit is the same as the value, there's not going to be any kind of break or discontinuity in the graph. Simply put, it's going to be filled in as it normally is. So again, that is not a discontinuity at x equals 4. Now, the horizontal asymptote, you might notice, was not part of this post-it note discussion. That's because horizontal asymptotes are y values, and discontinuities only occur at x values. Another way to put it is that you don't have to pick up your pencil as you approach that horizontal asymptote. So again, horizontal asymptotes are not discontinuities, mainly because they are not x values.
All right, so let's summarize these discontinuities, of course, that are being described to these limit statements. So in your notes, you're going to want to either put this with each of the corresponding x values or perhaps just kind of make a new spot. But I want to make sure you know that at x equals -3, we have definitely found a point discontinuity. So at x equals -3, you got a point discontinuity. Of course, that's because the left-hand limit, which equals the right-hand limit, does not equal the value. You know, we got a problem here. There's a limit, but it's not equal to the value. We call that point discontinuity. How about at x equals 0? At x equals 0, we've already found what's called a jump discontinuity. Now, jump discontinuities can be described with limits. If you think about it, the left-hand limit would have to be different from the right-hand limit. If the left side is not equal to the right side, then you're jumping. And we call that a jump discontinuity. And then we got x equals 2. X equals 2, as was discussed, is an infinite discontinuity. Kind of a little bit easier to see and describe. That's simply because the limit is equal to infinity. But make sure you realize that that's as x approaches that c value, which again, for our example, was x equals 0. Now, at the end of the graph, we kind of brought up the antidote to discontinuities, right? It's if you don't have a discontinuity, we would say that the graph is continuous. But the reason the graph is continuous is because the limit is equal to the value. So the limit is the intended height, and that actually equals the actual value. Now, I always like to preview something that we'll be doing tomorrow, but still pay attention. That way we can jump into this tomorrow. You see, we don't like discontinuities, so we want to fix them. So some of these discontinuities, or maybe we should say one of these discontinuities, is fixable, and it would be point discontinuity. Just kind of jot that down, that point discontinuity is fixable. You're going to find out that it's fixable because the limit exists. Jump discontinuity. So do you realize that it's not fixable? Well, it's because the limit does not exist. So if I don't have a limit in the first place, I'm not going to be able to fix the discontinuity. It's kind of too messed up to fix. It's because there's no limit. It's the same with infinite discontinuity. It's not fixable. It does not have a limit. So again, you're going to learn tomorrow that we're going to use the limit to do our fixing. Continuous doesn't need fixed. Okay, that's because the limit is already the same as the value. So we already know that discontinuities occur visually on a graph, but do we realize that they also occur algebraically when you have a bad number? What kind of bad numbers are we aware of when it comes to fractions? Yeah, a zero in the denominator, right? So what we want to do is we want to realize that the good old zero in the denominator that has always been bad is going to fit right into our conversation on discontinuities. Let's focus on the denominator. What am I doing here? I'm factoring it, right? Why am I factoring it? Okay, because really I'm getting myself ready to think about what makes the denominator equal 0. What makes the denominator equal 0? That's pretty easy. That's just -3 and 3. What you want to realize is that those are my two bad numbers. Honestly, those are my two locations for discontinuities. Now, what gets a little tricky for students is realizing that we already know the location, but how am I going to figure out the classification? Okay, I already know that something's happening at -3, but what's happening? Okay, use some of your prior knowledge. Remember that if you have a repeated factor that's from last year, that is a hole in the graph. Of course, this year that's a point discontinuity, but again, I can still use that concept that if I have a repeated factor, I'm going to be getting a hole in the graph at my bad number. Using today's language, you got point discontinuity at x equals -3. And again, I was able to deduce that because of the repeated factor. So what's going on with my other bad number? Is it also a point discontinuity? Well, don't overdo it, okay? My x plus 3, honestly, it cancels out, but that leaves me with just 1 over x minus 3. It leaves me with more of a standard 0 in the denominator. I'm talking about just a standard vertical asymptote. If you get a 0 in the denominator and there's no repeated factor, okay, yeah, that's always been a sign of a vertical asymptote. But you got to realize it's at x equals 3. Okay, now of course using today's language, that's infinite discontinuity. So I got infinite discontinuity at x equals 3. Now I was able to do that, honestly, just kind of using some algebra. But this is calculus class, so we want to try to state what is happening here using some limit notation. That gets a little bit more fun. Okay, can I describe the point discontinuity? Okay, well, I think so. I just got to try to get limit involved. I kind of have to almost force myself to write the limit notation. Okay, x approaching. Okay, now I don't have to try to go reinvent the wheel. This is the place where the bad stuff's happening, so that means x is approaching -3. How do I find the limit as x approaches -3? Okay, well, I'm going to still factor my numerator and denominator. I'm going to cross it off, and I'm going to create this this revised version of my function. And if you plug into your revised version, now you kind of get rid of the 0 in the denominator. I mean, you're going to actually get -6 in the denominator. Well, more specifically, you're going to get -1/6. Well, students, that's the limit. That's the actual, I should say, that's the intended value. Now, what I just did was I wrote a limit statement, but it still doesn't actually sort of finalize that there's point discontinuity, but I do need this limit statement. So what I got is the intended value is -1/6. What about the actual value? This is not a limit statement, but it is notation. So I'm going to make a value statement. I'm going to I'll go ahead and name it so you know what f of -3 is trying to say. What's the value at -3? Well, kids, remember that -3 is a bad number. We kind of already established that from the beginning. Well, that's because it doesn't have a defined value. I just need to say that. I need to say that -3 is not defined. And now we can say officially that this is point discontinuity. Why? Because the value doesn't equal the limit. There is no value, so there's no way it's going to equal the limit. Okay, but essentially there's a hole in the graph. How about infinite discontinuity? Could you write the infinite discontinuity using limit notation? If we were in class together, I would have you guys do this on your own. Yeah, go ahead, try to fill it in. You don't have to recreate it. We are approaching the number 3. It's this number 3. Okay, what's happening is we approach 3. Well, there's the intended height, I should say. What's the intended height as I approach 3 is going to plus or minus infinity. We just wrote a limit statement that describes infinite discontinuity.